All right, so we're just going to continue on with more gas law problems. So here's our next one. We're going to underline all of our givens just like we have been doing. So 4.00 moles, 5.40 atmospheres, volume of 120 liters. What is the temperature? So we are looking for temperature. Well, this one's a pretty easy one because you don't have to figure out the units figure out the variables based on the units. It just tells you everything. So the first thing you would notice when you're labeling is that this is moles. So this is going to be N because we know that N is moles in our gas laws. Okay. This specifically says it's a pressure of 5.0 atmospheres, volume of 120 liters, and then we're looking for temperature. So, like I said in the last video, you automatically know here that you need to use the ideal gas law because moles is in the problem, okay? If moles was not in the problem, then we could try to decide between the other ones. Another way to tell, you might have noticed, is that we only have one of everything. Okay, the ideal gas law is a moment in time, where the other four that we're studying are comparisons before and after a change or before and after a stimulus. So here you only have one of everything. You don't have P1, P2, you just have P. Okay, so that's another way to tell that you need the ideal gas law. Whatever works best for you, that's what you should do. So this one we're going to use the ideal gas law, which is PV equals nRT and then circle what you're looking for. Here we are looking for temperature. And what do we need to do to get temperature by itself here? Okay, how do we solve for temperature? Now, hopefully you remember this from algebra, but when letters or variables are written very just close to each other, that means they're multiplied, okay? So that means that temperature is multiplied by both R and T. Temperature is multiplied by both R and N. Okay, so in order to get temperature by itself, you have to divide by N and you have to divide by R. So I'm going to do that on both sides. And that means N and R will cancel here. And you'll end up with just T. So I'll go ahead and erase those. Okay, and now we plug in our variables. So we have P is 5.40 atmospheres. And we're going to multiply that by our V, which is 120. Oops. And then on the bottom, you're going to have moles, which is 4.00. And then R. So R, hopefully you noticed when you were looking at the doc, is something we call the ideal gas constant. Let's see if I can find that. So the ideal gas constant has different values depending on its units, okay? So when you're looking at this, you see that here all the liters are the same, all the moles are the same, and all the kelvins are the same. So the only thing that's going to change is the units for pressure, okay? If you look back on your unit or variable chart, you see that pressure can be in atmospheres, it can be in mmHg, or it can be in kilopascals, which is kPa. You'll also notice that in order for the ideal gas law to happen, you have to have volume in liters and you have to have temperature in Kelvin. Okay, so anything else you would have to do a conversion. So here, you have to pick an R value to plug in here. The way you pick an R value is you look at your units for pressure in the question. Okay, so we have atmospheres here. So which one is atmospheres? The first one. Okay, so since you have atmospheres here, you plug in this number. So I'll plug in 0.082. And then you just solve. But one thing, and if you have me as a teacher, you have heard this so many times already this year. You have to put everything in parentheses when you put it into your calculator. Most specifically, you have to put the stuff in the bottom in parentheses when you plug it into your calculator. If you do not do that, you will get the wrong answer. So please make sure you are doing that. Okay? And then you should get something that looks like this. I'm going to double check that. Yep. So it comes out to 1973.2 and so on. I did 1970 for SigFix because all of the givens have 3. Again, like I said in the last video, we're not going to be too picky about that. So just do your best on that one. If you had written 1973, I don't think any of us are going to get miffed about that. So I think that is great. All right, so let's go to the next one. So again, start exactly the same way you always do. You underline your givens and then label them. So we have 3 givens and we're looking for new pressure. Okay, this says assume the volume of the container is constant. We know that if we don't have any volumes. You'll also sometimes see that they give you the same volume twice, but if you just don't even notice that and use a different law, it comes out the same. It's fine. So let's go to our unit chart and figure out what these variables are. So here we have kPa. kPa is kilopascal, which is a pressure. Okay, so that is the one that we will pick. So this is going to be P1. And then we have, this specifically says temperature of 35. However, we know, we already learned last video, but also from this chart, that temperature must be in Kelvin. So you should cross this out and add 273 to it. So 35 plus 273. 308 Kelvin. And that's going to be our initial temperature, so T1. And then we heat it to 230, and that one people might not remember to convert because it's already so big, but you still need to convert it. So 230 plus 273 is 503. So it's 503 Kelvin. And that's T2. Pressure, P2. So if we have P1, T1, all these P's and T's, no moles, so that means we must be using this law, Gay-Lussac's law. So just like with Charles's law, I do find it easier for kids if you start by cross multiplying. So you do P1 times T2. And then P2 times T1. So now you have it all in a straight line. Circle what you're looking for. We're looking for P2. So we'll circle P2. In order to get P2 by itself, you have to divide by T1. I don't know why this is so slanted all of a sudden, but go with it. The T1s will cancel over here, so I'll erase them, and we'll have this nice formula to plug stuff into. So now, nice and easy, we plug in what we've already labeled. So here we have 84.0 kPa. Times T2. Make sure, again, just like last time that we used T, that you're using T2. T2 is 503. And then divide by T1, which is 308. .84 times 503 divided by 308, and that gives us 137 kPa. So let's stop and see if this makes sense. Okay, just like we did in the last video. So we didn't give you a simulation this week on this, but knowing what pressure is and knowing how temperature affects molecules, you can think it through. Okay, so one thing that you've know from the past 2 weeks is that when temperature increases, that means the molecules are moving faster. That means the kinetic energy is moving faster. Like the kinetic energy is higher. So the molecules are moving faster. You also know that pressure is the collisions that the molecules have with the sides of a container. So, what do you think should happen if temperature goes up? The molecules are moving faster, they'll collide more. Okay, so that means pressure should go up. So think that through. So if we heated the temperature, which we did here, we went from 308 Kelvin to 503 Kelvin. If we heat the temperature, that means the pressure should also go up. Did it? Yes. We went from 84 to 137 kPa. So again, if you didn't and you're sitting here and you're reasoning through it and it doesn't end up making sense, check your temperatures. The biggest mistake people make in these problems is putting their temperatures in the wrong place. Okay, I'm going to stop here and do the next two problems in another video.